Okay, so from this week, we're building up to a kind of final main topic of the course, which is reinforcement learning, especially multi-agent reinforcement learning. Um, so from this video, we're going to be starting to kind of move towards that. So this week, we're going to be moving towards something called stochastic games, which are Markov chains, which are jointly controlled by a bunch of players who are playing a game. First, we're going to start by looking at what's called Markov decision processes, which are equivalent to stochastic games with one player. So we're back into a one-player decision theory setting. So back where we started right at the beginning of week one, studying one player trying to optimize something. But now we're going to make the thing that they're trying to optimize significantly more complicated. So we're going to spend a few videos looking at just this setting because there's quite a lot to say about it and it's quite interesting. And then later this week, we're going to put the players back in. Okay, so Markov decision process is roughly a Markov chain which is controlled by an agent who is trying to optimize something. So let's remind you what a Markov chain is. And okay, so specifically, we're doing Markov chains in discrete time. So what this is we have a finite set of states, which are called Q, and then also a transition function that says that whatever state we're in, we get a probability distribution over all of the states that we could transition to in the next step. Or equivalently, it's a conditional probability of the next state given the current state. Okay, now, what that means is that for any choice of initial state that we could be in, if we kind of drop the Markov chain into a particular state, we can run it and it will run stochastically. It's going to generate an infinite sequence of states Q1, Q2, and so on, and this will keep running forever. And so what we get is basically a probability distribution over all of these infinite sequences of states it could generate. The key thing about the Markov chain is that it's memoryless, which means that the next state depends only on the current state. Or to say this in extremely precise probability theory terms, the next state is conditionally independent of past states given the current state. Okay, so that's an ordinary plain Markov chain. Now let's look at controlled Markov chains. So now these are Markov chains where the transitions partially depend on the actions of a controller or an agent. So as well as a Markov chain, we're going to have a set of available actions, which we could also call controls, which are called A. And we're going to modify the transition function to say that for every pair of the current state and the current action, we're going to get a distribution over next states. Or equivalently, this is a conditional distribution on the next state given the current state and the current action. Okay, now, the question is, what is this agent or controller? Well, we can say what is a policy for them. A policy for them, and this is what we have so far been calling a strategy, but in this world it's traditional to call this a policy. A policy is an assignment of a choice of action in every possible state. So it's a thing that tells the agent what to do. So for every state, it says which action they should take. And we can have deterministic policies, or we can also have stochastic policies. So this is a bit different to what we normally call a mixed strategy. So a kind of mixed strategy would be a distribution over deterministic, like pure strategies. But this is a bit different. This is a conditional choice of action given the current state. That's a subtly different thing. So if I wrote the other thing, it would be delta open brackets Q arrows A close brackets. For Markov decision processes, which is what we're building towards, usually we focus on deterministic policies. That's generally enough in this setting. Okay, now similarly to before, if we have a choice of start state plus a policy, either deterministic or a stochastic policy, that's going to stochastically generate an infinite sequence of states. So we kind of for every state, we take that state together with the action that the policy chooses in that state, and then that gives us a distribution on the next state. Okay, Now, okay, so this says what it means for a Markov chain to be controlled, but so far we have nothing for the agent to optimize, so we have no way to say whether this policy is good or not. So for that, we need to attach payoffs, and this leads us to the definition of a Markov decision process. So a Markov decision process is the same thing, except whenever the Markov chain does a transition, so whenever we transition to a new state, the agent is awarded some payoff. So, so now the transition function gets this type for every state, for the current state and the current action, we get a joint distribution on the next state and the payoff. So that is to say we have a conditional joint distribution of the next state and the payoff given the current state and the action. So what this means is now if we have a choice of initial state and a policy, this thing is going to stochastically generate two things, an infinite sequence of states and also an infinite sequence of payoffs. And remember, the Markov property still holds here. So everything is both the next state, both the next state and the next payoff are conditionally independent of whatever happened in the past, given the present. Okay, now the question is, what is the agent's goal? Well, we already know about discount factors because we already studied repeated games. So we're going to do the same trick. We're going to pick a discount factor, which is some number between 0 and 1, and then we can form this geometric series of the payoffs. And so the point of the discount factor is that it makes this thing convergent, so this thing is a finite value. And then we say that the agent's goal is to maximize the expectation of that, so the expected total discounted payoff. I'm about to show you a picture of this so you can kind of clearly visualize what these things look like. So let me say that a Markov decision process can be seen as a kind of repeated game with one player, where the strategy is the policy. So this is a little bit different to other kinds of game that we've seen before. So specifically, this doesn't match our existing definition of an infinitely repeated game in two different ways. So first of all, previously, we forced all of the randomness in the rules of the game to happen up front. So we have a kind of single move of nature at the beginning, and then after that, the game evolves deterministically other than any randomness that could be done by the players. So in theory, we could do the same thing, but it starts to get increasingly impractical. So at this point, we're going to really start seeing that the transitions that happen during the kind of evolution of this Markov chain, the randomness is happening right now at the current transition. So at every stage, we're kind of doing some randomness. Probably more importantly, the difference is that Markov decision processes are games of, I've written the wrong thing in the slides here. These are games of imperfect recall. So that is to say that the policy is only allowed to depend on the current state. So we kind of see the players as forgetful. Even though players have made choices in the past where they knew the current state, they forget what those past states were. And they're only allowed to use the knowledge of the current state. So so this is the Markov property for policies or for strategies, and that's an instance of imperfect recall. So until now, we've seen imperfect recall as a kind of weird thing that makes our life slightly difficult. But the Markov property is a specific kind of imperfect recall that actually makes our life easier. Okay, so here's a picture of what one of these things look like. So I have finally, you'll be happy to know, made an example that looks somewhat resembling artificial intelligence. So let's talk about high-level control of a robot. So let's say a robot has a battery level and it can sense two states of its battery, but it can be high level, battery level can be high or low. And at each point, the robot either can do work, which is, I guess, trying to fulfill its assigned task, whatever that is, and that gives us a fixed reward, or it can choose to recharge, which gives it no reward, but it returns it to the high charge level. And if the battery level falls too low, so if it does work in the low battery state, there is a risk that it becomes stuck. And if it becomes stuck, then we say it needs to be rescued. It incurs a large negative reward that kind of punishes it for getting stuck, and then it returns to the high battery state because we've rescued it and recharged its battery. So you can draw this thing as a graph or as a kind of transition system where so on every edge we need to say, so we have our states here, high and low, and then each one of these arrows we say what is the action that is being done, what is the probability that this arrow is the one that we follow given that action, and then also what is the payoff that we get for following this arrow. So for example, in the high state we could choose to work, and then with probability 1/2 we follow this arrow and get a payoff of 1 and then land back in the high state, or with probability 1/2 we follow this arrow, we also get a payoff of 1 but we fall into the low state. If we're in the low state, if we work, then with probability 1/2 we land in the low state again, we successfully achieve the task, we get a payoff of 1, but with a probability 50% we get stuck and we follow this arrow, which is where we get rescued, and then we go back into the high state where we incur a utility of -10. We also have the choice to recharge in both states. So if we're in the high state and we choose to recharge, then with probability 1 we land still in the high state but we get no payoff, and if we're in the low state then we can recharge, and with probability 1 we land in the high state and we still get no payoff. So there's quite a lot of information packed into this little diagram, but this is a complete specification of a Markov decision process. So a policy for the robot here would be a choice of, for each state, do we work or do we recharge? So an example of a policy would be, if you're in the high state, then work. If you're in the low state, then recharge.